Hello there. In today's lecture, I'll give you several examples of BCH codes. Here's my first example of BCH codes. Let Q be 2, and n be 2 to the r minus 1, where r is at least 2. Then n and q are coprime, and the BCH parameter m is equal to r. Let beta be a generator of the multiplicative group of g of 2 to the r. So beta has order n, which is 2 to the r minus 1. The first two cyclotomic cosets of 2 modulo n are C0, which is comprised of 0, and C1, which is comprised of these powers of 2. So C1 has size r. Let g of x be the minimal polynomial of beta over g of 2. So the roots of g of x are precisely the powers beta to the I, as I ranges over all elements in C1. Then g of x has degree r and is the canonical generator for a binary BCH code C of length 2 to the r minus 1, dimension 2 to the r minus 1 minus r, and design distance 3. The design distance is 3 because C1 has two consecutive integers, 1 and 2. Hence, by the BCH bound, C has distance at least 3. Now, a PCM for C must be an R by 2 to the r minus 1 binary matrix H, whose columns are non-zero and distinct, since the distance of C is at least 3. Since there are exactly 2 to the r minus 1 non-zero binary vectors of length r, each must appear exactly once as a column of H. So we recognize that C is a binary Hamming code of order r, with distance exactly 3. Since C is a BCH code, it's also a cyclic code. It follows that all binary Hamming codes are cyclic up to equivalence. Here is a second example of a BCH code. Let Q be 2 and n be 23. Then the BCH parameter is m equals 11. And that's because 2 to the 11 is 1 modulo 23. There are 3 cyclotomic cosets of 2 modulo 23. These are C0, C1, and C5. C1 and C5 each have size 11. In fact, the factorization of x to the 23 minus 1 over g of 2 is x plus 1 times the product of these two degree 11 irreducible polynomials. Let beta be an element of order 23 in the multiplicative group of g of 2 to the 11. And let g of x be the minimal polynomial of beta over g of 2. Then g of x has degree 11, and so is the canonical generator for a binary BCH code C of length 23 and dimension 23 minus 11, which is 12. Among the roots of g of x are the 4 consecutive powers of beta, namely beta, beta squared, beta cubed, and beta to the 4th. And so C has design distance 5, and hence by the BCH bound, its distance is at least 5. Now g of x is one of these two degree 11 factors of x to the 23 minus 1. Both these factors have weight 7. And so, since g of x is itself a code word, the distance of C is at most 7. I'll state as a fact, which I won't prove, that C is equivalent to the binary Golay code C23. So even though C23 itself is not cyclic, it is equivalent to a cyclic code. Here is a third example of a BCH code. Let Q be 2 and n be 2 to the 16 minus 1, which is 65,535. Then n and q are coprime, and the BCH parameter is m equals 16. Let gf2 to the 16 be represented as polynomials over Z2 modulo this degree 16 irreducible polynomial. It turns out that alpha is a generator of the multiplicative group of gf2 to the 16. So beta equals alpha is an element of order 2 to the 16 minus 1. I've listed here some of the cyclotomic cosets of 2 modulo 65,535. Note that the cosets C1, C3, C5, C7, up to C23 are distinct, and each has size 16. Now, let g of x be the product of the minimal polynomials of powers of beta, as the powers range over the odd numbers from 1 to 23. There are 12 such odd numbers, and each of these minimal polynomials has degree 16. And so the degree of g is 12 times 16, which is 192. So g of x is the canonical generator for a binary BCH code C of length 65,535, dimension 65535 minus 192, which is 65,343. Among the roots of g of x are 24 consecutive powers of beta, from beta to the first to beta to the 24th. And so the BCH code C has design distance 25, and by the BCH bound, its distance is at least 25. Let's write down the canonical generator for the BCH code in example 3. The field gf2 to the 16 has characteristic p equals 2 and extension degree m equals 16. The elements of gf2 to the 16 are the set of polynomials over Z2 of degree at most 15 modulo this irreducible polynomial of degree 16. We saw this representation of gf2 to the 16 in lecture V2e, where we checked that A, I'm writing A here instead of alpha, is a generator of the multiplicative group of gf2 to the 16. We'll take beta to be A, so n is q to the m minus 1, which is 65,535. Now the canonical generator G of the BCH code is the product of the minimal polynomials of the 12 odd powers of A, from the first power to the 23rd power. So we need to compute 12 minimal polynomials and then multiply them together. This piece of maple code accomplishes this. For each odd number, let's say j, between 1 and 23, maple computes the minimal polynomial of a to the j as a product of the linear factors whose roots are the conjugates of a to the j with respect to gf2. Here are the 12 minimal polynomials. Maple multiplies these together to find this degree 192 polynomial g as the canonical generator for the BCH code. As a sanity check, we verify that g is a divisor of x to the n minus 1 over gf2. It turns out that shortenings of the previous BCH code are used in practice. Let me define the shortening of a code. So let C be a systematic NKD code over GFQ, and let T be a positive integer less than K. Let C primed be the code obtained by shortening C in its first T coordinate positions, by which I mean the following. Take all code words in C that have a 0 in the first T coordinate positions, and then delete those coordinates. The claim is that C primed as a linear code of length n minus t, dimension k minus t, and distance at least d. Here's a short proof of this claim. Since C is systematic, it has a generator matrix in standard form. Let G primed be the matrix obtained by deleting the first t rows of G, and then deleting the first t columns of the leftover matrix. You can check that the matrix G primed is a generator matrix for C primed. So, since G primed has k minus t rows, n minus t columns, and its rank is k minus t, it follows that C primed is a linear code over GFQ of length n minus t and dimension k minus t. It's clear that shortening C doesn't decrease its distance, and so C primed has distance at least d. Recall that the code C in example 3 on slide 166 is a binary BCH code of length 65,535, dimension 65,343, and distance at least 25. This code C is systematic, and that's because C has a generator matrix of this form, where the first row is g of x, whose leftmost entry is a 1, and the other rows are right cyclic shifts of g of x. In fact, all cyclic codes are systematic. Consider the shortened code C primed obtained by shortening C in its first 33,135 coordinate positions. Then C primed is a binary code of length 65,535 minus t, which is 32,400, and dimension 65,343 minus t, which is 32,208, and its distance is at least 25. This shortened BCH code C primed is used together with an LDPC code, which we won't cover in this course, in the DVB S2 standard for digital video broadcasting for satellites. My last example will describe the codes used in QR codes. Let Q be 2 and N be 15, so N and Q are coprime, and the BCH parameter is M equals 4. GF2 to the 4 is represented in the usual way, and beta, which is alpha, has order 15, which is N. I'll let G of x be the product of the minimal polynomials of beta, beta cubed, and beta to the 5th over GF2. These minimal polynomials were listed on slide 151. So G of x has degree 10 and is the canonical generator for a binary BCH code C of length 15 and dimension 15 minus 10, which is 5. Among the roots of G of x are the 6 consecutive powers of beta, and so C has design distance 7, and therefore distance at least 7. Now G of x is itself a code word, and it has weight 7. So C has distance exactly 7, and is a 3-error correcting code. This code C is used in QR codes to encode the format data. I'll mention that there are 32 formats in the QR code standard, and the number of code words in C is 2 to the 5, which is 32. So each format can be encoded using a unique code word in C. We saw in example 2 on slide 165 that this degree 11 polynomial G of x is the canonical generator for a BCH code that I'm calling B23 that has length 23, dimension 12, and distance 7. I mentioned that this code is equivalent to the binary Golay code C23. Let E23 be the set of even weight code words in B23. then you can check that E23 is a binary cyclic code of length 23, dimension 11, and distance 8, with canonical generator g of x times x plus 1. Let S23 be the 1868 binary code obtained by shortening E23 in its first 5 coordinate positions. This code S23 is used to encode the version data in QR codes. There are 34 versions in the QR standard, and 2 to the 6, which is 64 code words in S23. Lastly, a 255, 231, 25 Reed-Solomon code over GF2 to the 8 is used for the payload in QR codes. More precisely, 2 shortenings of this Reed-Solomon code are used to encode the payload data. We'll see this Reed-Solomon code in slide 175. I'll conclude this chapter on BCH codes by mentioning that several efficient algorithms have been designed for decoding BCH codes. We don't have the time to study them, but you can find one in the course textbook. Instead, in the next chapter, we'll see a decoding algorithm for a family of BCH codes called Reed-Solomon codes.
This concludes the chapter on BCH codes. In the next video lecture, we'll define Reed-Solomon codes, which are a special family of BCH codes. We'll explain why Reed-Solomon codes are especially good at correcting burst errors. Have a wonderful day.